Yeah, last year it's been 1 year. I seriously can't believe it. It's been 1 year. We gave this presentation. So it's called Bitcoin Mining, a technical overview. Yeah, Bitshala is focused on technical education. This this Saturday, we're getting joined by a Bitcoin mining industry leader. And before that, it's important for you to understand Bitcoin mining itself. And yep, let's start. Overview of the presentation. So I'll cover the first few, I think the first three or maybe four bullet points. And Bala, would you be able to take over from there? I don't think I'll be able to share a lot of anecdotes.
Yeah, I can.
Super, super. Thank you so much. Yep. Let's start. So yeah, overview of a block. Bitcoin is made of blocks. Bitcoin is a blockchain, and it is the only blockchain that matters, and there are good reasons for that. So yeah, in case any of you is entirely new to Bitcoin, what I think I can tell you is that you can imagine Bitcoin to be a monument. This is the analogy I love. The Genesis block is the foundation. It was the first block ever to be mined, and Satoshi mined it, hard coded it, and it had 50 Bitcoins. And from there, Bitcoin has been working as a decentralized system where even the second block itself was mined not by Satoshi, or probably not. I might be missing that detail. Anyway, yeah. So how Bitcoin mining works is that miners compete to find the next block, and how they do that is by trying to find the valid block hash. And how the valid block hash is found is by using the block header. This is the block header. Like, I'll walk over the details of the block itself. So the block header is what is used to generate a hash, and it is iterated over using the nonce value. So yeah, before getting into the details, a Bitcoin blocks is a list of transactions. Like, that's the summary of a Bitcoin block, and block header itself is the summary of those transactions. So transactions, Bitcoin transactions are me sending you Bitcoins, Alice sending Bitcoins to Bob, and how that works is that you use UTXOs in the previous block, in one of the previous blocks in the blockchain. So maybe I can show you mempool.space quickly just to visualize it better. Yeah, so this is how Bitcoin looks. So current block height is 903,677, and yeah, it's linked to this block through the block hash. And whenever a new block is found, like, these are the competing blocks right now, and this is still yet to be mined. So any miner can pick this block up, iterate over the block header, and whenever they find the valid block hash, which means a certain number of zeros in the block hash, then they are able to mine the next block. We can quickly walk over these details. Like, this is the transaction. So transactions is just uh, uh, users of Bitcoin creating a new transaction using the UTXO from the previous transactions using digital signatures. So whenever a new transaction is created, uh, I don't think we have the time to go over the Bitcoin white paper, but it has a beautiful visualization. Let me just open it quickly in case we have the time to cover it later. But yeah, that's how transactions look like. And those transactions are sent across the network. Yeah, this is that visual. Yeah, so this is how a transaction looks like. So whenever a owner wants to, like, I think this is a better transaction look like. Whenever an owner wants to spend his Bitcoin, they use the transaction from the previous ownership. So for example, the owner wants private key signs this transaction, and using that signature, the previous transaction is linked to the original transaction. And yeah, I don't know if I was able to convey the point, but yeah, anyway, the transactions are listed in the block by the miner using from the mempool. So whenever I create a transaction and I send it across the network, it gets included in the mempool of the nodes, and those nodes, some of them are mining nodes, so they pick up those transactions and include it in the block. And then the block header is constructed by the miner. So the block header itself includes these four data structures. So one is metadata, which includes the block version number, timestamp, and difficulty. Block version number, as far as I can remember, is just the version of the blockchain, and yeah, it's a standard to And yeah, please feel free to correct me if anyone has a better clarity over what block version number is. But I think it's the current version of the software release of latest Bitcoin core. Yeah, and timestamp is a data structure to of the block and yeah, it also has I think it has two data fields. If I can't, I'm sorry guys if I making a lot of technical mistakes right now. But timestamp is the measure of the Bitcoin block in that blockchain. So timestamp is used across different setups to create time locks as well. And yeah, it gives you the the time in the time chain. So there is no external clock to the time chain. Like there is no 8 p.m., 9 p.m. in Bitcoin. It's just block time, which is every block which is found on average in 10 minutes, and that's hard coded because that's how the system operates, and that is possible because of the difficulty adjustment. So whenever there are new miners joining the system, the difficulty goes up, which means that the required number of zeros in the block hash goes up. So it becomes harder for the miners to find the right nonce. And nonce is just a number, 4-byte number, which is iterated over, and it is called the proof of work puzzle. It's literally just you can imagine it like a hamster uh, like game. I don't know if you know this game where hamsters keep popping up, and so the human has to hammer them down back. So if whenever the miner just keeps stamp, like you can imagine like digging in the ground, and whenever they're able to find that particular nonce, which is just a random number, they just iterate over it 1 2 3 4 5, and whenever they find the right number, that's the valid nonce, and hence the valid block hash, hence the valid block, and it is propagated across the network. Yep, and this is the hash from the previous block. This is what links this block to the previous block. I think this is that visualization. So this is the current block, and we are visualizing it, and the block hash is this block's hash. So you can imagine it like you can use this block, hash it, which will give the block header of this block, and it goes in here. So this is what gives the validity to the rest of the network that this block is playing by the rules of Bitcoin, and this is being mined on top of the previous block. And block header, so SPV, simple payment verified nodes, which users can use. Bitcoin miners can't do it. Bitcoin miners need to validate the whole blockchain. But yeah, simple SPV nodes are run by a lot of users, which might not have the memory to run the whole to save the whole blockchain, and they can only save the block header. It provides like ease of use in terms of verifying the blockchain, but it makes the compromise of trusting a full node, which it uses to receive those block headers. Yeah, then that Merkle root. Yeah, Merkle root is a tree structure of transactions. So I might be able to show you that visualization. So Merkle root is like a summary of the transaction in that particular block. Yeah, this is how it looks. So you can imagine it like I'm trying to maximize the size. Yeah. Yeah, these are the transactions, and you hash them together. Like when you hash two transactions, you create a hash of that couple of transactions, and depending on number of transactions, if there's an odd number, it is used separately, and then you create a Merkle root, uh, which is the summary of those transactions, and yeah, it's unique to the transaction list. So if any transaction gets changed, the Merkle root gets changed. So that's how no Merkle root can be meddled with. And I think just to like zoom back a little, the whole point of using proof of work is so that if any of these previous blocks get meddled with, if any node in the network tries to manipulate previous blocks, then uh, the whenever they find the next block and propagate it across, the rest of the network will be able to see that the hash from the previous block is different, because hash requires Merkle root, and yeah, Merkle root is dependent on all the transactions on the previous blocks, and that's how Bitcoin validates consensus rules. So yeah, proof of work is the magic, and difficulty adjustment is the magic within proof of work, through which Bitcoin is able to sustain and operate as a decentralized system, where any attacker, if they want to change the current state of the blockchain, will need to have more computation power than 51% of the network. because otherwise the rest of the network will keep on moving ahead, and unless you have 51%, you will be forced to play by the rules, because it will eventually become too expensive for you to manipulate any transaction, or try to change any block, or yeah, create your own blockchain as well. I think the a common question I've faced is that like, why can't I create my own blockchain, right? This is the most common trope in the altcoin world, that they want to come up with their own blockchains. So the security of Bitcoin comes from a couple of things. One is the users themselves, people who are running nodes, people who are using Bitcoin, people who value Bitcoin. The second is the expensive computational cost required to use or sustain the Bitcoin blockchain. So any other blockchain is being run by a group of individuals, like on a very practical level, and on other, like, more technical reasons, it becomes almost uh, redundant to even do that, because the whole point of using blockchain is so that it becomes expensive for an attacker to try to come up with a competing chain. So why would you want to do that for anything else other than a decentralized system? Is a question, at least. And I think there are nuances to this. Like Andres Antonopoulos, I think one of his talks about how if he were to name Bitcoin, he would call it Trustnet, because he says money is the first application. And I might not be fully versed with Andres Antonopoulos on ideas of how he sees Bitcoin's evolution. But one thing is for sure, that Bitcoin is money, and for any money to have a decentralized system, it will require a blockchain, which is the Bitcoin blockchain. And for anything else fancy, which Ethereum or whatever other Solana and ecosystems try to do, does not require a blockchain. And Nostr is the living proof of that. We have a protocol for censorship resistant media without requiring a blockchain. And I think the other interesting bit that I might be able to share, and yes, if someone has better clarity over this, please feel to share. Please feel to correct me. The closest to blockchain we have is Git. Git itself uses hashes to verify the validity of previous commits to the software. So that has been the closest to verification of history using hashes. And after that, we have Bitcoin. And the reason that Bitcoin uses proof of work and blockchain is so that it wants to make itself expensive. Yeah, it wants to make itself expensive because Bitcoin should be hard to mine, because money is hard to find. Okay, I'll take a quick pause here. Uh, yeah, if someone has any questions, yeah, I think it's important for all of us to understand how a block looks. And yeah, it's a page in the book, right? You can imagine it like a page in the book. The monument analogy is not likable, and those pages are linked to each other using the hash in those blocks. And those hash is found uh, by iterating over the nonce value. There is a beautiful video that I've watched a few times. I haven't watched it in a while now, but watch it every few months. I think it's a strong recommendation from me. It's on Learn Me a Bitcoin on SHA-256. It's a beautiful, beautiful video on how SHA-256 works, and I think that will, like, give you just a profound appreciation for how hash functions work, how Bitcoin is using hash function. Yeah, that's the one. Yeah, keep sharing this in case I'm spamming.
I was interested to find
I
out more about
apologize.
SHA-256.
Wait, I'll share it in the chat. Yeah, SHA-256, I think the way I explain it to people, you can imagine it like on a very, very, like, explain like I am five story of SHA-256, is that it just takes a big number. So in Bitcoin, a lot of the things are big numbers. Like a private key is just a big number, nothing fancy, it's just a big number. And uh, a block header itself is a big number, right? And when you put it through the hash function of SHA-256, what you are doing with it is just creating entropy or creating noise. You are throwing numbers around, and you throw it in a way where there is no way for anyone else other than brute force to come up with a number of certain zeros. So how a valid block hash looks is that it has certain number of zeros in itself. So whenever there's a less number of miners, you will need less number of zeros so that it becomes easier to find, or there is higher probability of finding it with less computation. But whenever there is a lot of miners, right, and we are in a adoption stage where mining and hash rate is just increasing by the day. So we're not the difficulty adjustment is always going up. We're not ever like we face it in stages, like in matter of weeks or probably months. But in matter of years, the hash rate is definitely going up. So the difficulty adjustment keeps going up. And what that does is that it creates a requirement for the miners to produce a long string of zeros in the valid block hash. So SHA-256, because of how it works, like you can watch that video, it just throws the number around using prime numbers and square roots, and it's just beautiful. Yeah, Amol asked the question: is our Bitcoin node mining by default, or do we need a specific hardware like Bitax or a miner? No, so our Bitcoin node in terms of I have run it on my laptop. So if you download it from bitcoin.org, it's not a mining node. And to the best of my knowledge, Umbrel, the most popular plug and play implementation of a Bitcoin node, is does not allow mining node as a default as well. And a mining node is only required by a miner because mining node requires extra computation of collecting transactions and like running through uh, nonsense. Yeah, Bala, do you have any input for that?
Yeah, it used to be that the miner and node were one and the same, but sometime a while ago, like in the early 2012s, they were separated. So your node is not a miner. Your node just verifies transactions. It doesn't mine.
Yeah, yep. And there are nuances to this as well. I might be able to share it later, but I remember um, there are different types of nodes, right? So mining nodes necessarily like collect transactions. Uh, but yeah, every other node as a user does not require you to uh, yeah, like hash the block header, which is extra computation. So most of the Bitcoin. So yeah, do we need a specific hardware like Bitax or a miner? So yeah, with Bitax, I think you need to run a mining node. I might be mistaken. So I think the workshop on fifth will clear this for me. But yeah, I think it requires you to run a mining node. Uh, Second question: does miner store full blockchain or is it connected to the network through our full node? Yes, so any Bitcoin miner will need to store the full blockchain if they want to like verify from the Genesis block. Otherwise, they are trusting someone else's full node. Or is it connected to the network through our full node? Yes, yeah. So I think that's what you mean, right? So if a miner is not running a full node, then they are using someone else's full node to provide them with the valid blockchain. And that usually will be expensive for them because if it's not the valid blockchain, then they are mining on top of a attacker's chain, which is redundant. And yeah, for most mining businesses, it definitely is necessary for them to run a full blockchain. After how many blocks can the miner spend the blocks as reward? Yeah, after 100 blocks, this is hard coded. So whenever a miner finds a block, they have to wait minimum 100 blocks to be able to spend those bitcoins that they found in that block. Yep. And yeah, Bala.
Yeah, the miner, they have their own full nodes, and they have um, it is not exactly the same as a plebs node. So they have different their own customized mempool policies, and they have their own customized way of constructing a block. So it depends upon the mining pool.
Yeah. And yeah, I think like mempool.space has mining pool with each blocks, like which might be blocked. I've not gone too deep ever into like details of which node the particular mining pool is running. But like for example, pool found this block and it has this much hash rate. Uh, yeah. What else can we find out which is interesting? I don't know what this is. 71 and 7%. This is I think blocks. Okay, they found 7 blocks in the last 24 hours, which is 5%. I think current the number of daily blocks which are found. Um, yeah. Yep. Mempool.space is a treasure hunt in itself. There's a lot of things happening in mempool dot space. Yeah, I think overall I would like also
And
recommend.
just a minor clarification here. If I'm not mistaken, the consensus majority is handled by the nodes, right? Like the 51%, or the majority of, or rather, the longest chain in the blockchain is sort of looked at via what most number of nodes are uh, are referring to, not the miners per se, right?
So the longest chain or the most proof of work chain is considered the valid chain. So that's how we arrive at consensus. So any node, like 51% of nodes do not matter. So to each his own node, I think that's the rule of thumb. When you're running a Bitcoin node, you are not relying on any other node. You are literally just using the tip of the blockchain as your source of truth, and how you arrive at that is proof of work. So you don't need to like trust any other node. You don't need consensus from like the rest of the nodes. The consensus rule is a different subject. Like consensus rule in itself is the underlying assumption on how Bitcoin operates and what are the rules through which Bitcoin transactions are validated. But the number of nodes, the percentage of nodes do not matter to the individual node particular blockchain. Where 51% matters is the computation cost or the hash rate. So the more hash rate gets concentrated with one entity, let's say one entity is able to capture 51% of the hash rate, the next block they will be able to mine like with half guarantee, right? Like half the time they will find the next block. And if the rest of the network is like spread out, let's say 5% hash rate, 10%, 30%, whatever, right? Then it becomes difficult for them to catch up. So what that presents as the risk is that the entity with the 51% hash rate will be able to manipulate or double spend the Bitcoin. Like how they will do that is that suppose I have the 51% hash rate, I create a transaction, it gets included in the block. Because I am the entity with the hash rate, I get to mine the next block. Like there is a very strong probability, right? 50% of the times I will be mining the next block. So I mine that next block and I have sent 10 Bitcoin, sorry, received 10 Bitcoins, right? I've received 10 Bitcoins from someone. But now sorry, I've sent 10 Bitcoins. But because
Basically, you
now,
record a double spend transaction in your in your chain, right?
yes, yes. And how you do that is because you can change the history of the blockchain. Like, let's say its current block height is 100, right? Let's for a very simple example. I mine the 101 and 102 block, but now I spend my Bitcoin again and I mine from the 100th block again. So I've changed the history of the past one or two blocks. Does that make sense?
Yeah,
Like,
as in, I mean, what I was trying to what I was trying to get clarification more was on the lines of, let's say a node changes the consensus rules, like what happened in the block size wars.
yeah,
The block size wars was essentially won by the original original guys with the fixed block size, and it did not get evolved. The one of the reason has been that because no, because the majority of the nodes did not agree for the increased block size.
yeah.
It was not necessarily because they had the majority of the hash power, isn't it?
Uh, no, I don't think that was the reason. It was more on the consensus block size itself, like the limitations of block size. So the default block size was 1 MB
No,
originally,
the
but then yeah, Bala, go ahead. Bala, your audio broke. Can you? Uh, yeah, I'm not able to hear Bala's. Can someone else confirm?
Yeah, I'm not able to hear him either.
Okay. But yeah, anyway, I'll continue. So yeah, so the consensus was regarding block size itself. So the block
uh,
size originally the default size was, and then it was 4 MB because of like
Mm.
SegWit. But the debate was whether to increase the block size by a hard
because
fork.
Right.
Bala, you might want to try joining again. There's some disturbance, I
Yeah, I
think.
think his lines is very patchy.
Yeah, yeah, yeah. Bala, there seems to be some network issue. But yeah, the whole contention, like I haven't read the block size watch discussing it, like myself as well. Like I need to read it. But to the
Mm-hmm.
best of my research, what I know is that the debate and dilemma of the block size was regarding scaling of Bitcoin, because Bitcoin currently as well, right, can't scale on the base layer on the
Of course,
on chain,
right,
because it can't
right,
contain entire financial transactions on the blockchain. And the solution that big blockers came with is just like brute force, right? Like just increase the block size, like more transactions. So the primary defense against was that if you do that, it becomes a precedent. So it like, and some projects did that, like Bitcoin XT, and yeah, like a couple of others as well, which increase the block size to 8 MB, 16 MB, whatever. And what that does is that it makes expensive for individuals to run nodes. If you do that, eventually there will only be so many nodes, and like
right.
running nodes is already,
Centralization problem
yeah,
will
yeah,
start to
exactly, yeah,
occur.
exactly. And I think like one of the ways I've understood the centralization problem is that there is no technical solution to it. Of course, like Bitcoin centralization is a uh, constant effort. There is no one solution like magic bullet to decentralization. But block size wars has told us that like increasing block size can't be the solution, because that way you can always keep doing that. That's just a brute force, no creative solution. And
Right,
that like why Bitcoin mining had a central piece or like stakeholding in that discussion was because miners are incentivized to increase block space, because it will increase the transaction fee. So Bitcoin
right,
miners, because they were large businesses, had a lot of influence. But in terms of like consensus, they don't have a say. Like consensus itself is defined by the nodes, not Bitcoin miners. Bitcoin miners are like one of the analogies that helps me is the highway analogy, that they are the road constructors. If like they make the roads through which the cars go, but the cars themselves do not need like the highways just help the cars go from A to B. So there will always be more highway constructors, so you can either take one route or two route or three route. And that's where Bitcoin mining decentralization is important. That itself is also a dilemma right now, because most of the mining companies are US companies. Yeah, currently it's like if US government really wants to call like the biggest heads of Bitcoin mining to a meeting, like more than 60% of hash rate will be in that meeting. Like five heads of the like of those companies, and you have boom, you have like one entity holding more than 51% of hash rate. So it's a constant
mm,
struggle. Like, there is no technical solution to it. And yeah, I think I just to close in on like Bitcoin mining. I think like I always this picture and the other one, Merkle root itself as well. Like Merkle tree is a wider concept in computer science, not just Bitcoin. And yeah, I recommend a lot of people to just meditate on this picture, because I might not be able to best explain it right now. Maybe I'll do a better job next time. But yeah, this picture is one of the most like iconic pictures in Bitcoin. And yeah, it tells you how one transaction is linked to the next transaction using digital signatures. And this picture tells you how one block is linked to the previous block. Yeah, and I think for me, it has really helped me defeat that argument of why blockchain does not help in any other system. Like Bitcoin blockchain is designed to make a money which is outside of control of any entity, right? Not just government, like anybody, nobody gets to enforce their rules on Bitcoin, because it's expensive, because the blocks are mined using hashes from previous blocks, and by doing proof of work on them. And it's a comparative lottery. Like anybody can participate if they have cheaper energy, better hardware, uh, yeah, and a better ability to raise capital. Like one of the subjects in this book that I've been reading is covered of how like a lot of large companies have raised capital to manage volatility. So it's a more dynamic game than I had originally thought. Yeah, yeah, I can go into nuances of that, but I think I'll take a pause here, because uh, yeah, maybe after this, I'll hand over to Bala. Bala, are you able to? Oh, Bala just joined. Super. Yeah. Hey, Bala.
Hi, sorry, connection issues.
No worries, no worries. Yeah, I'll cover like couple of slides, and then I'll. By the way, we're already into so long. But yeah, we'll cover this quickly. So yeah, mining overview. Why do we do mining? Why is it important? Because it secures the Bitcoin network without a central authority. There is no mining cartel, because anybody with free energy can enter Bitcoin mining. Currently, the state of mining is that most of the Bitcoin mining companies are huge US public listed companies. which is because of the US capital markets more than Bitcoin as a system itself. Yeah, miners expend energy by performing multiple number of double SHA-256 hashes per second. So when I mentioned SHA-256 or block hash, they actually do a double SHA-256, and there is a very simple security reason for doing it twice, like double. But yeah, that covers like the essence of it. Like you hash it twice using SHA-256 of hashes per second proof of work, incentivizes miners to secure and facilitate decentralized consensus by awarding them a coin-based reward. So yeah, this is why miners mine. It also enforces the scheduled supply of bitcoins. So yeah, difficulty adjustment enforces the fixed supply, right? A fixed supply of Bitcoin that we all know and love. That the next block can only be found in 10 minutes. So the difficulty adjustment makes sure of that. A block is said to be mined if the following condition satisfies the following conditions. So yeah, you can meditate over this later. I'll quickly just cover this. So how it is done is that the data is the block header. You add the nonce value and you iterate over. Like this is the hammer, right? It's tuck, 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 tuck. You just keep changing the nonce value. You find this hash, then you double hash it. It should be lesser than the target value. And target value is set by the previous target value. So the current target value is the target maximum, which is like the most difficult number to find in the history of all hashes, divided by the difficulty, the current difficulty. And how the current difficulty is calculated is yeah, is this. Yeah, so data is block header except nonce. Nonce is a 32-bit unsigned integer. Target is a 256-bit unsigned integer. Yeah, so yeah, target is the number of yeah, you can imagine it as a dartboard, and target is the bullseye. And yeah, the bigger the target is, the easier it is for the next block. And the more miners enter, the target gets becomes smaller and smaller, so that it becomes difficult for the miner to find the block. Yeah, that's about it. I think yeah, I've covered all of this. Yeah, you can go over this picture, like the slide is available. I think you really need to. Yeah. Yeah, Bala, would you like to cover this mining probabilities?
Yeah.
Yep, yep.
Just a minute.
Yeah, probability, by the way, was one of my favorites in school, and it like I think for me when I was studying Bitcoin as well, the whole SHA-256 and Bitcoin mining and how probability work makes it work, right? How because every miner needs to find that random number by just brute force. Like there is no other way to do it, and it is based on probability. Like the only way to do it is to iterate over the number. Yeah, I'll take a pause here. Yeah, Bala.
Yeah. So Shreyan gave you a brief overview of how mining happens. We just went through difficulties and target and stuff. So now we'll have a basic look at the probabilities, because mining itself is a probabilistic event. Uh, as you saw in the previous slides, we are trying to find a, double SHA-256 value which is less than a target. So there is no other way to do it but to uh, keep changing the nonce and try to hash it once again. So you cannot calculate a value which is less than the target. So there is no deterministic way of doing it. You have to keep trying, and this action of keeping try the where we keep on trying is a probabilistic event. So what this can be in mathematical terms, this can be understood as a random event. Given a difficulty d, which is a number, the probability of finding a block can be calculated to be 1 by 2 power 32 times d. So this is this is how you calculate the probability of finding a block. This is actually the math that is used when you go to some sites where you can like check like you plan to buy a miner, and you want to see how what is the probability or what is the what is the probability of you hitting a block. So there are sites which give you some numbers. So this is the math that they also have behind the site.
So they just take your hash rate and use it over this probability to give you a number. So basically, if you have a miner with a hash rate h and you mine it for a time period t, let's say 2 years, 3 months, 6 months, whatever might be the time, you plug that in and it will give you a number. So that is a number of blocks that you are likely to find with your miner. So this is the calculation that goes on behind the sites. Um, so if there are some math our folks in there, you would appreciate that this process is a Poisson process. You can Poisson process is a mathematical concept, and it has a few properties. Uh, if whatever process that you are looking at in your case satisfies these categories or conditions that has to be met by a Poisson process, then your own process can be called as a Poisson process. That's what we do here. So basically, Bitcoin mining satisfies the three major criteria that qualify a process to be a Poisson process. So, firstly, the event which you are trying to which you are trying to understand, or which you are trying to derive a probability for, should occur independently of each other. So, in our case, that means for the event of finding a hash which is less than the target uh, is independent of the previous hash, or the like the previous block that you found, or the future. So uh, f- uh, none of the previous blocks that you have found sort of implements, like sort of affects your probability for the next hash. So it doesn't mean that you found, because you found like the previous 10 blocks consequently, you are more likely to find the 11th block. It doesn't work like that. So for each and every time that you give a go at it, it's an independent trial or independent event. So that is one thing that is special about the mining algorithm. Then uh, the average rate of the event should remain constant over time. So based upon the hash rate, we have in our algorithm fixed a definite time interval like 10 minutes. So the event of finding a block happens roughly over 10 minutes. If at all there is more hash rate added, we change the difficulty so that we come back to the 10-minute block intervals. So that criteria also, Bitcoin mining also meets that criteria, and two events cannot occur exactly at the same time. So a miner cannot find two hashes which is less than the target at the same time. So because he is doing performing double SHA, and the double SHA will give you only one number. It will not give you two numbers, because it's a defined well defined hashing event. So he cannot find two hashes at the same time. So basically, a mining conforms or checks all the boxes of a Poisson process. That's why we use Poisson to understand mining. Next slide, please.
Yep, yep, yep. I had a quick basic question, like it might be a stupid question, like what exactly is hash rate? Like a very rudimentary question. Like I've always been curious. Is it the like I my attempt at it is that is the unit of electricity? Uh,
The number of hashes that your miner can perform per second.
hmm, hmm.
So now, for example, a BitX can do close to 750 to 800 giga hashes per second.
Right, right, right,
Uh,
right,
the latest ant miner probably can do somewhere around 500 to 600 tera hashes per second.
right. And if we quickly go to the mempool, so for example, like F2 pool found the latest block right now, and it mentions that hash rate is 98.1 like
Exactly.
exahashes per second. So this is the hashes. This is the hash rate of the pool, right?
Yeah, of the pool.
Yep, yep, yep. Yep. Thanks.
Yeah.
Okay. Yeah. Next slide.
So yeah, based on this, we can do some calculations. So
Sorry to interrupt, Bala. If I'm not mistaken, there is also an hash rate to indicate the current difficulty level as well, right? Is that so?
uh, no, hash rates and difficulty are completely different stuffs. So difficulty is something that the network calculates or puts up for you. Hash rate is whatever is brought on to the network. So hash rate is something that is plugged in by the users of the network. The network is not at all aware of the hash rate. So the network doesn't know what a hash rate is. All that it knows is the difficulty number and yeah, the rate at which blocks are being found. So the difficulty adjustment will happen if the rate at which the blocks are being found does not stick to its defined 10-minute intervals. So then it will kick in the algorithm and the difficulty will be either revised upwards or downwards depending on it.
Okay, okay. There's not like a direct correlation that as the hash rate increases, the difficulty increases, or there's not like a direct formula as such, right?
No, there
Mm.
is no. Yeah.
Okay,
Yeah.
okay.
The difficulty is calculated using the previous difficulty, and the difficulty itself uses target as the reference. So the target value itself, because when like there's more hash rate, the like you can imagine it like this. So whenever the hash rate increases, like for some reason in the next 1 hour, 2 hour, the next blocks will be found rapidly, right? Because of the increased hash rate. So
Hmm.
in the next 2016 blocks will be found very soon, and because of like the difficulty adjustment being hard coded, the average time has to be 2 weeks. Like it has to be 2016 blocks found in 2 weeks. Like that's the hard code in the network. And so the target value now will be calculated based on that. So I spent time on this like a couple of years ago. It's like, maybe I'm not able to explain it as good, but I think like this formula is what helps. Like this is how the difficulty is calculated, but the hash rate itself is like an external factor. Like the network, yeah, like Balaput does not is not aware of hash rate. Yeah, it
Okay,
uses the fact that the previous 2016 blocks were found rapidly or very slow as as the measure for recalculating instead of the hash rate itself. Yep,
Yes.
gotcha, gotcha.
yep. Next slide, Bala.
Yeah.
Yeah, there's no chance we are covering probabilities of these word distribution. Okay, yeah,
So I'll just run through those. Um, no, no. Can you go to the previous slide? Yeah.
yeah.
So in this example, like we try to calculate um, what would be the chance or probability of a miner with a certain hash and a given difficulty. Uh, what would be the probability of finding a block? So that we ran through using the Poisson's equation. Uh, so basically, uh, so the inference is that the inference that we can get from this um, get from this thing is that um, okay uh, so if you put this miner onto the network and start hashing, uh, we can like observe uh, uh, I'm trying to figure out a way to simply put it. uh, So if a miner were to observe like many 24-hour mining data of his, given the mining parameters, he has a 5% probability of having found approximately 53 blocks. So if you look at this probability mass function, so that's what this plot sort of says you. I don't think we have enough time to go into the technicals of it. Uh, Basically, the there is something called as probability mass function, and there is something called as probability distribution function. So these two are used to get an idea of what number of blocks um, that a given hash rate can find in a given time. So if you see, have a look at the bar plots there. So basically, it says that given the hash rate and the time, we can find like there is a 26% probability of finding somewhere between 50 blocks in the given time. So the given for in this calculation we have taken an example of 24 hours. So basically that means that if you throw 228 exahashes at a difficulty of 56.87 t uh, uh, of the network, what we can get is that we are sure, or we can expect to win about the chances are that you will win 50 blocks with a percentage of like 26.8. So there is a 26% probability of you winning 50 blocks in the given time period. So that's the odds that are stacked against you. Uh, I know it's a little difficult to get these things around. Communication is also a little bit tricky with these concepts. So yeah,
Yeah.
if at all anyone needs any clarification, you can get back to us. We'll probably have a
Okay.
detailed discussion. Yeah, next.
One basic question, Bala. I think difficulty of 86.87 T just means this T is a metric of number here, right? It's just a number, right? Difficulty.
Um, Difficulty is just a minute. So it's it is calculated as the target max divided by the current target. So
Yeah.
it's a number. uh,
Yeah.
so I'll get you the exact units.
Mm-hmm. Yeah, I think the format might, of course, like that's a computer science detail, but difficulty itself is just.
Bala, yeah,
Yep, yep.
Yeah, yeah.
yeah. Just one question, guys. Are we confident that in the example that you talked about in this, probability or normal distribution, it is actually 50 blocks?
Yeah.
I'm just getting confused. Shouldn't it be one block?
No, no.
Okay.
The probability distribution function gives you uh, uh, what it tries to convey to you is that in a with a given hash rate and the given difficulty in a 24-hour time window, you will be able to find 50 or 55 blocks in total with a probability of 26 point something. So it's not like
Uh,
100%
so
guarantee that you will find 50 blocks,
yes.
but
So Bala, that's where actually I'm getting a little confused. So probability is always between 0 to 1. Okay. So 26% is basically 0.26, right? Okay. Now, my confusion is, see, when you say that you will get 50 blocks, so 50 itself is like 1 plus 2 plus 3 like this. So if I have to actually find the probability of getting a one block,
yeah.
right?
No,
Okay.
that is
Or maybe I am decoding it wrong. That's what my confusion is coming from actually.
yeah. You cannot find the direct probability of finding one block.
Okay.
When you want to examine these things, you can only get the probability distribution function and probability mass function. So they are not direct
Okay.
probabilities.
Got it. Understood, boss. Understood now.
Yeah.
Okay.
Yep. Yeah, maybe in future we'll have a separate session recording on mining probabilities. Like it's a pretty dense subject. But yeah, I think we are at 9 mark. Is there like I think 5 minutes. Is there something specific, Bala? Do you think we can cover?
Yeah, can you run through them? Yeah, can you go to slide number, uh, yeah, 1 minute, 12?
Yeah.
Yeah. So basically, we skipped a bunch of stuffs about pool mining, how pools work, and how pools communicate, and all those things. So there is a pool target and those stuffs. We'll just get to the interesting part. So this is how pooled mining evolved. Basically, as Amol asked, in the beginning, both your node acted as both a verifier and a miner. So it simultaneously verified transactions that and blocks that it got from its peers, and it also had a built-in miner. So whenever you spun up a node, it also started mining in the background. That's how Satoshi got all these huge coins. So whenever he ran his core software, it also kept mining in the background. It also that single piece of software was everything. So it was a node, it was a wallet, and it was a miner, and it was also it was also acting as an Electrum server. It was also acting as a GUI interface. So that was in 2010, around that time. And later people started to realize that it is in order to scale this stuff, we need to remove key components of the whole mining, like the whole Bitcoin ecosystem, and then develop them separately. That was the idea behind it. So initially, there was no concept of pool, and every miner was mining on their own. When you opened your Bitcoin core, it always ran on its own, and it mined on its own. It did not communicate with any others to share their hashes to come to mine. So this concept of pool mining probably originated in 2010 with the get work protocol. Then by 2012, something called as get block template was introduced, and later this get block template was upgraded to Stratum B1. So Stratum B1 is the mining protocol that runs even today. Uh, so it has had a long history, and now we are since 2019 we are trying to upgrade or move from Stratum B1 to Stratum B2. Next slide.
Yep, yep.
Uh, so get get block templates. These are all earlier versions of it. Uh, so the Getwork template was the first ever pool mining protocol. So it was also inside the core software itself. Uh, Shreyan, can you go to the Getwork
Yeah.
slide number 13? Yeah. So this was also like it was technically, if you look at it, it was based on HTTP with JSON encoding. That was the best possible available tech at the time. Uh, it The algorithm was designed such that the nonce and timestamp fields in your block template were used to search for a solution to the block. So that is the basic outlook of Getwork. Probably the problems was it was not able to keep up with the increasing number of people that are entering with their hash rate, because only nonce and timestamp was not enough. People quickly ran out of options, and they were not able to find the block. And it also led to block template centralization. Means people were not able to when you get into a pool, only the pool operator had the template, and you were not able to control any, like, decide what goes into the block or not. So that was a big problem. And then long polling, uh, it was a network issue, and miners were not able to communicate effectively to the pool and get information. as to whether a block has been found, whether their whatever work they submitted was valid, and that kind of stuff. Yeah, next slide. So
Yeah.
then get block template came into picture. This was also a part of the core itself. Now the new thing that they added to it was the search space was slightly expanded. You had the Coinbase was added to it. So you had a like you can enter stuff into the Coinbase data field, and you can create an expanded search space. Uh, Again, it also had the same sort of issues as with your get work. It was also based on HTTP. It was not suitable for low level efficient communication and stuff. Then you had the same block template centralization problem that was never solved. Um, then it also had the polling problem. The miners were not able to get real-time information from the pool, so that led to a lot of wastages. So these sorts of issues persisted. And then Stratum V1 came into picture. Uh, so there was some serious changes to it. Uh, this is when when Stratum V1 came into picture, was mining separated out from Bitcoin Core. Uh, so this was earlier versions were based on HTTP. That means the communication between the pool, the miner were all based on HTTP protocol. Now it was based on layer 4 of the OSI model. Then the search space was whatever search space was adopted in the get block template was used. Now you have nonce, timestamps, and Coinbase. Now, because of the TCP IP protocol, the pools can proactively push mining jobs to the miners, so that the pools you have to understand that the pools are the one that have a overview or look at the network. As a miner who is doing the job, the miner does not have a node attached to it, so it doesn't know what happens in the network. So it just hashes whatever stuff the pool sends to it. So now because of this TCP/IP, now the pool can like maintain communication with the miner, and it can constantly update the miner as to what sort of job it should do. So these were all the new developments of V1, and they are all stand even to this day. This is the protocol on which our whole hash rate is based on. So it keeps chugging along, but it has a lot of problems. The communications in it are unencrypted. Basically, the TCP IP communications are not encrypted. Even today, it's not encrypted. Because of it, there is a chance of man-in-the-middle attack. Then, if you look at the TCP IP protocol itself, the number of connections that you can make, like in a pool, because a pool has to accept connections from a lot of workers or miners, it cannot. There is a limit to how many connections it can accept. So that kind of problems still are there. Of course, since the very first iteration of mining protocol, block template centralization still remains even in V1. And the miner cannot decide what goes into a block. He can only work or hash a block a template that is being pushed to him. So these are all the problems that still exist in V1. Yeah, so now we are working on V2. Uh, Basically, it has improved connection scalability on the pool side. So uh, the the biggest technical focus or achievement of V2 is that it is able to improve the connection scalability, because we saw in the last slide that V1 has scalability issues with TCP/IP connections. Then it also has managed to reduce latency and bandwidth consumption, and it has also encrypted the connection between miner and the pool. These are all the three major changes that V2 has brought in. So because of these changes, you have better scalability for pools and better efficient communication between the pool and the miner. Then there is a lessened man in the middle kind of attacks. And finally, you have this decentralized block template generation. So one of the last or uh, Segwit, in Segwit, the major focuses are on transaction malleability, but the poster child of Segwit is block size increase. Similarly, for V2, all other stuffs are the actual working horses of V2, but the poster child is a decentralized block template generation. Yeah, it is now it's being actively worked on, and one of our Bitshala fellows, Bitalu, he contributes to Stratum V2. Uh, Potential bottlenecks. The biggest bottleneck is that miners have to upgrade their firmware, so they have to upgrade from V1 to V2, and we don't know. We really don't know how many miners are interested in this. So that is a big bottleneck. And community awareness. As I said earlier, the poster child for V2 among the community members is decentralized block template generation. But actually, the critical or major infrastructure changes are something else. So there is lack of awareness within the community for V2. So
Yeah.
yeah.
Would we be able to cover datum at all, Bala? Because
No.
and okay,
Datum is not V2, Stratum V2. Datum is Stratum V1. Except that they have worked out a way so that they can decentralize block template construction. So yeah, what the first 4 points are first four features of Stratum V1 is the same for V Datum also. Except that they have devised a workaround for block template centralization issue.
okay,
Yeah,
nice. Yeah, thank you so much, Bala.
yeah.
Yeah, I think
But just a quick question there. These are all optional upgrades, right? These are not like mandatory that every single miner that's there out there has to simultaneously upgrade to the new protocol. These are most likely optional, right?
Yeah, they are optional. Means there is still there is no consensus, or the V2 is not completely built out yet. The work is still ongoing, and once the devs are able to demonstrate uh, clear like stability and technical and economic advantages, there won't be adoption from the miners themselves.
I'm sorry, did you say there won't be?
Yeah. It's devs are finding it currently. Devs are finding it difficult to convince the miners to switch over. It is a huge upgrade for them because, basically, if you see at Ant Miner as a company has to upgrade their firmware for each and every of their mining devices out there. So they have to upgrade their firmware, then they have to push the updates, and the pool operators have to pick up that update, upgrade each and every ASIC out there. So it's a huge operation.
Okay, got it. I mean, they're going to evaluate the cost
Yeah,
basis and cost versus benefit.
yeah, they have to. They will. They have. It has to make economic sense to them to upgrade.
Gotcha. Okay, thank you.
Yeah.
yep. Yeah, thank you so much, Bala. And I think yeah, we're towards the end of this session. Yeah, I just wanted to talk about pool mining a bit. I think pool mining, like Bala said, during early 2010s, and I think it emerged as a way for the hash reward variance to reduce so that uh, individual miners are incentivized better. But yeah, I don't know, think we have the time to cover this in detail. Yeah, and maybe I can show you around a gridless a bit. Gridless has been doing. Africa, and yeah, they have like this is low key information, but I have expressed India in interest in India a little. And yeah, this is where like the wider Bitcoin mining ecosystem and Indian Bitcoiners come in. Bitcoin mining in India currently is not like happening at all, and I think like it will require massive educational effort. Uh, yeah, but it's inevitable, right? All of us understand that India has a lot of energy potential with nuclear, thermo, hydro, solar, wind, like name it, right? But if someone has any insights over that, please like feel free to share now and later as well. Um, yeah, it's an active area of research and entrepreneurship. Okay, thank you so much, guys. Yeah, if you're in Bangalore, I'll meet you there. And yeah, have a good night. Thank you so much for joining.